Scientists like to categorize things and classify things. It helps us to make sense of overwhelming amounts of information. So we can classify matter by its physical state. There are 3 common states of matter: solid, liquid, and gas. We are familiar with water in all 3 of its physical states. As a solid, we call it ice. Liquid water, we just call water. And in the gas state, we call it steam. So the difference between these 3 states of matter has to do with the interactions between the particles, how they're free to move, and how much space is between them. So in a solid, all of the particles are fixed relative to each other. This water molecule cannot move relative to that molecule. It's stuck there. So there's also 3 states of students. Right now you guys are in the solid state. You're a nice crystalline solid. Everybody's in there, sitting in their desks, and you're all in rows, right? So if you look at the person to your right, that person was sitting to your right 5 minutes ago too. We're not milling about. In a solid, the particles are fixed in place. Are they absolutely motionless? No. Just like you are not absolutely motionless. Everyone is at least breathing, right? Nobody's passed out yet. So you're breathing. You're wiggling, you're looking back and forth, you're taking notes, right? Little movements. That's what happens with a solid. The particles are moving, but they're not moving relative to the other particles. They're just like vibrating, oscillating, just, like an antsy child jiggling. I gotta move. I can't get up because my mom's gonna yell at me, but I'm gonna sit here, right? And we'll find out that at a higher temperature, they move more. They get more and more agitated.
Is that where we get the microwave from?
Yes, a microwave does have impact with that. And so the microwave is a form of electromagnetic radiation that will cause the water molecules to oscillate and move faster. And that is expressed as heat. And so the microwave really works by increasing that kinetic energy of the water molecules. There's a lot of cool things that science can explain that you use in your everyday life. So feel free to ask me questions about that. So in a liquid, when the ice cube melts, now the water molecules are still close together. I call them touchingly close. You could reach out and touch the person next to you, right? We're touchingly close, maybe a little more than we would like to be in this tiny room. They're still very close together, but now they can slide around and move relative to each other. This is when the students are in lab. So those of you who had the first section, we were in lab, and for a lot of that time you were sitting still, but when we're doing an experiment, we get up and we move around. We're still close to each other, but now we're moving around. This is the gas state, where the particles are separated by larger distances. This is when class is over and the students go out the door, and you go off in all different directions, and you maybe don't see each other again until we come back tomorrow. So that's the gas state. These particles are having no interaction with each other. They're no longer touchingly close. You can't reach out and touch someone. And they're just going off independently. So these slides kind of just say the same thing over and over again. I kind of already went over this. So solid state, atoms are close together, fixed locations, don't move relative to each other. This is why solids have a fixed shape. Think about an ice cube. You get it out of the tray, you put it in a bowl, you put it on the floor, it retains its shape, right? Same shape, same volume. We can divide solids into crystalline solids or amorphous solids depending on how the particles are arranged. I mentioned you guys are in the crystalline solid state right now because there's a pattern to your arrangement. You're sitting in rows. That would be like this. There's a long-range, three-dimensional order to how the particles are arranged. Amorphous means without shape. This is more like kindergartners sitting on the rug for their teacher to have story time. They're not going to sit down in rows naturally. It's just going to be all jumbled together. So that's amorphous, without shape. In the liquid state, again, the things are touchingly close. So they have a fixed volume because they're still close together. But a liquid will assume the shape of its container. You take a glass of water and you pour it into a bowl. Its volume stays the same, but the shape of it changes because the particles can move relative to each other.
Mrs. King,
Yes?
what determines whether a solid is, like I mentioned, crystalline and amorphous? Like what determines
That's a good question. What determines whether a given solid is crystalline or amorphous? It has to do with the interactions that occur between the atoms or molecules, what type of interaction they are. It can also depend on how the solid was formed. If it crystallized slowly out of solution, or if it was a metal that was molten and cooled quickly, it might be amorphous. And so substances can sometimes be in different forms. So the gas state, the molecules are separated from each other and they're moving relative to each other. Because of the space between the particles, gases can change in their volume. Liquids and solids do not do that appreciably, but gases can change quite a bit. So gases always take on the volume of the container, and they also take on the shape of the container. Gases are compressible. So in a gas, because there's a lot of empty space between the particles, you can squeeze the container and squeeze the gas particles closer together and make the volumes smaller. That doesn't work with a liquid. The particles are already touchingly close. You cannot squeeze them any closer. So liquids and solids are generally not compressible. This is a summary of what we've just talked about. Do you have any questions? I'll take that as a no.
I was going to say on the gas, does the temperature affect how much is compressible?
Yes, the temperature of a gas has a large effect on how compressible the gas is. And when you compress a gas, it's going to require some pressure, some force. It's not going to just, you look at it and say, oh, compress yourself. You're going to have to do something to it. And we have an entire chapter devoted to gases. So we will definitely learn more about that. Any other questions?